Okay, so let us continue from what we discussed last week. So we have been discussing the main topic of inter-process communication. That means, uh, I mean, till before this, we thought processes were running independently, but now we understand that processes can talk to each other or can have to communicate with each other, and the OS gives us several mechanisms using which two processes can communicate with each other. So we have started discussing the first of such mechanisms, which is shared memory. So if you see in the picture, so this is the memory. So we know that a part of the memory, the kernel itself will run. Then let's say you have two processes, process A and process B. Now the standard memory that you have when you write a C program, that is only, say process A is a C program which is using some memory, and that memory will be specific to process A only. But now we are looking at a different kind of shared memory, a different kind of memory which can be shared between multiple cooperating processes. And so, I mean, your program itself cannot create such a memory. You have to take the help of the OS, and therefore you have to do some system calls. So we discussed these system calls last week, like SHM get is the system call by which you ask for a certain amount of shared memory, and you also give the permissions, what permissions you want, access permissions you want for that memory, and so on. So this SHM get is usually done by one process. After that, any process which wants to use that shared memory uses SHM attach to attach the memory segment to the address space of this process. And then you can use the memory. Once this is done, you can use the memory like any other memory. And at the end, you should detach. I mean, a process should detach the shared memory and mark it for deletion. So typically that process which will create the memory using SHM get, usually that process will mark it for deletion. Okay, so yeah, so this is about shared memory. Now let us just take see a practical example of two processes which needs to communicate via shared memory. So as that practical example, we will look at a producer-consumer problem. So I think the problem is pretty obvious from the name. So there are two processes, a producer and a consumer. Producer produces information that is consumed by the consumer. Now this is a very abstract problem. There are many instantiations of a producer-consumer problem as written in this slide. Let's say a compiler produces assembly code and an assembler consumes it. Or a program produces lines to print, the print spool consumes, and so on, right? So we see producer consumer all around us. So suppose we want to emulate this producer consumer using two processes, which will communicate via a shared memory. First of all, I think it is very clear that this problem requires a shared memory because somewhere there has to be a buffer where the producer will produce items and the consumer will consume or read items from that buffer. So at the very least, that buffer needs to be shared, right? And apart from that buffer, there are a couple of other things which need to be shared. Let's see. Okay, so there are two variants of this problem. One is a bounded buffer problem. This is the buffer that you have is bounded. So the buffer can become full. Bounded means limited. It can become full. So here the producer may have to wait if the buffer is full, and the consumer has to wait if the buffer is empty. The other variant is unbounded buffer, where your buffer is kind of unlimited. So only the consumer can have to wait when the buffer is empty. Since the buffer never gets full, the producer never has to wait in the unbounded buffer problem. But in the bounded buffer, both have to wait. Okay. Okay. Before going into the details, let me just ask: in your networks course, have you come across something which also reminds you of producer-consumer problem? I mean, is it already done? It will of course come, but has it been done or it will come? That is what I'm understanding. So in your networks course till now, have you done anything which, or have you studied any topic which closely resembles this producer-consumer problem?
Sir, is it
Using
flow
software?
control problem?
Sorry?
Is it flow control problem, sir?
I could not understand.
Is it flow control problem, sir?
Flow control. Yeah. Okay. Okay, just one thing again. I mean, I would appreciate if instead of just starting to talk suddenly, you write in the chat. Okay, so yes, as Sandeep said, and also the person who spoke, yes, I was hinting at that flow control problem, sliding window protocol, and so on. So that is also, if you see, a producer-consumer problem. Again, understand the difference. In this, what we are discussing in this OS course, the producer-consumer problem is a bit simpler because the producer and consumer can share data. We will just see what kind of data is shared. But in a networks course, the same producer-consumer problem is much more complicated because the producer and consumer are running on two different machines and they cannot share data. Right. So whatever has to be told, like at some point maybe the producer needs to tell the consumer, or okay, at some point the consumer needs to tell the producer, slow down, I cannot take data at this speed. In a networks course, the consumer has no direct way of telling that to the producer, right? Because they are on two different machines. And therefore, you have lots of like a bit more complicated protocols like sliding window protocols and so on. Okay, so good that I hope you are, I mean, you are being able to mentally map what is being discussed in the OS course and the networks course because there are commonalities, especially in this segment where we are talking about two processes communicating. Anyway, coming back, in OS, this producer consumer problem is slightly simpler because we are assuming that there is a shared memory. So let's see how to implement this. Again, there are different ways of implementing it. This is one way. So let's say we implement that buffer as a circular array. Okay. So let's say it's an array of structures, whatever. So let's say we have the buffer size 10. So we are looking at a bounded buffer problem. So buffer size 10, and let's say every element is a structure with some data. It's okay. It can simply be int or some structure. Okay. Now, so this buffer, if you see, is in the shared memory. And because the producer and the consumer will need to coordinate, we have these two variables in and out. So in is the write position. That means the producer will write. So one question is, where should the producer write and where should the consumer read from? In is the write position. That means producer will start writing from in. And out is the read position. So the reader will start reading from out. Okay. So these in and out, so these are the three shared variables, the buffer itself, in and out. Now, I mean, it's simple. So yes. So index in is the next free position to write to. So this will be used by the producer. And index out is the next filled position to read from. This is used by the consumer. Now, of course, an important question is that the producer and both the producer and the consumer, they sometimes need to check if the buffer is full or empty. Right? So specifically, the producer will need to check if the buffer is full. If it is full, then it should not write anymore. On the other hand, the consumer has to check if the buffer is empty. So if the buffer is empty, it should not try to read. How to check if the buffer is empty or full? It's written in the slide. I mean, I think it's easily understandable. Now, one thing to note here is this is the correct implementation, but there is one small disadvantage. That is the way we are keeping this in and out. we will be able to use one less item than the buffer. Okay, so if our circular array or the buffer is of size buffer size, then we will be able to use buffer size minus 1 items. That is one small disadvantage. Otherwise, this implementation is correct. So now let's see what the producer and consumer does. Very simple. Here is the pseudocode. So both of them we are assuming will run in infinite loops. So while true. Okay, so they will go on producing and consuming items. So this is what the producer does. It first checks if the buffer is full. In plus 1 modulus buffer size. If this is equal to out, this means the buffer is full. So you do nothing. This is a semicolon here. Okay. So basically, nothing to do inside this loop. Just go on checking and waiting until the buffer is, as long as the buffer is full. If it is not full, then put your new produced item in buffer in this location, buffer in. Okay. And then increment in by 1, modulo buffer size, because buffer size is a circular buffer. That is about the producer. Now about the consumer. Again, simple. The consumer first checks if the buffer is empty. This is how to check. If in equal to out, then the buffer is empty. Then do nothing. Otherwise, remove an item from the buffer. Which position in the buffer? Out. Okay. So consume that item which is at buffer out. And then increment out by 1 modulo buffer size. Okay. So this is a correct solution, but one small disadvantage is one less item can be used. Okay. 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 Any questions? So if you have any questions, say. Otherwise, I have a question. But suppose we want to use that last element also. That means you want to use every element in the buffer. And can any of you think of a way in which it can be done? Specifically, maybe instead of in and out, will it help if we keep some other kind of information? Any thoughts? Okay, let me proceed. I think the answer is simple. So instead of in and out, if we just keep a count of how many positions in the buffer are being used, then that might help things. Let's see. So again, let's consider a circular buffer. Now suppose that we want to use all the buffer space. So just have an integer count, the number of filled buffers at present. And this integer count will be in the shared memory. Initially count is set to 0. And every time the producer increments, every time the producer produces an item, it will increase count by 1. Of course, where it will produce the new item, that for that in and out is there. Right? So it will continue to produce at in. So in is the point where the producer writes an item and then increments in by 1 modulo buffer size. And similarly, the consumer we will continue to read from out, and then it will increment out by 1 modulo buffer size. But additionally, we have this additional variable, shared variable count, which is incremented by the producer every time it produces an item and decremented by the consumer. Okay, so now it's like this, if you see. So just check that the checks for buffer empty and buffer full have changed. Now we are no longer using in and out to check if the buffer is full or empty. Rather, we are using this variable count. So now basically you have 4 shared things: the buffer, in, out, and count. All of these are shared between the producer and the consumer. Okay. So any questions till here? Okay, if not, let me proceed. So that is our discussion on shared memory. So shared memory is one of the mechanisms that the kernel provides for 2 processors to communicate with each other. Right. So now, and we have also seen a practical example of 2 processors which are actually dependent. That means they communicate with each other to get some work done. Okay. So shared memory is one type of IPC mechanism, inter-process communication mechanism. Let us look at another mechanism, which is called message passing. So again, message passing is also a mechanism for processors to communicate and synchronize their actions. So here we don't use shared variables, rather we directly use messages. So as if that you have two, say, two functions, send and receive. Using send, one process can send a message to another process, and using receive, another process can receive this message. Okay. So if you have this kind of a message passing system, then I mean, how does this work? Let's see. So this is the like a pictorial representation. So the kernel is maintaining a message queue. I mean, of course, message process A and B has to tell the kernel that we want to set up a message passing system. So the kernel will help them to maintain a message queue. So whatever message A sends will be stored in this queue, and process B can get them one by one. Again, I hope you are able to see commonality between what is possibly being discussed in the networks class and here. So again, the only difference is that this is in the same system. So, a part of the memory can be used to implement this message queue. Whereas in your networks course, the 2 processors are in 2 different systems. So there is nothing shared at all. Okay, so now the Linux kernel gives 2 ways of message passing. Actually, they are very similar still. Pipes and named pipes. So let's understand them. So a pipe usually acts as a medium to allow 2 processors to communicate. And this communication can be uni or bidirectional. This depends upon how you want it to be. Like you have to tell the kernel what kind of pipe you want to use. Now there are a couple of questions here which we will answer. Which 2 processors can communicate using a pipe? Does there have to be some relationship between the 2 processors which are trying to communicate using a pipe? For example, parent-child relation. That is one question. The other question is, can the pipes be used over a network? Yeah, the answer to the second question is that no, that is, I think, intuitive. So whatever we are discussing in this course, that cannot be used over a network. You are using it over like shared memory, pipes, etc. And how can you do similar things over a network that you are being taught in the networks course? But now let's understand the first thing, like which processes can use pipe? Does there need to be any relationship between two processes if they want to use pipe? Let's see. So first let's discuss ordinary pipes, then we will discuss named pipes. So an ordinary pipe cannot be accessed from outside the process. Cannot be accessed from outside the process. So typically, of course, if there is only one process, there is no, I guess, question of sending a message. So typically the use for a named pipe, the use for an ordinary pipe is that a parent has forked a child, and now that parent and the child want to communicate using this pipe. Right? So basically, this pipe can be used only between this parent and child. Any other unrelated process will not be able to use this pipe. So these pipes behave like FIFO queues. And yeah, I mean, actually, if you see the other picture, actually, the picture in the previous slide, this pipe itself is like implemented as a producer consumer problem, like what we discussed just now, right? So one process is the producer, one is the consumer. Yeah. So a producer writes to one end of the pipe, that is the right end, and the consumer reads from the other end, which is the read end of the pipe. And typically such pipes are unidirectional. So it is designated that which process will write and which process will read. So yeah, I mean, it's too simple, but this is how, like, you can solve the same producer consumer problem using pipes in this way. You have to first set up the pipe, right? And then after you do that, then it's typically very easy. Just one process will write to the pipe using send, another process will read from the pipe or consume from the pipe using receive. So the previous one was ordinary pipes, could be used only between a parent and its child. A slightly better or more useful mechanism is a named pipe. So first thing to note is a named pipe is accessed almost similar to a file. We will see some code snippet, but basically just like you access a file, a named pipe can be accessed that way. And this is important. Two processes, if they are communicating via a named pipe, then no parent-child relationship is necessary. Okay, so any two processes, of course, they have to know the common name of the pipe. Okay, so that's the point. I mean, last class when we were discussing, I think someone had also asked this important question. Again, see, we are talking about two cooperating processes communicating. So they must have some knowledge in common, some background knowledge. For example, in the shared memory case, there used to be a shared memory ID that needs to be known by both processes. So here also, if you are using a named pipe, and I mean the two processes are not parent-child, then both of them would need to know the name of that pipe, just to indicate, just like a file. So if you want multiple processes to read from a file, all the processes should know the name of that file or the path of that file. Here also, if multiple processes are wanting to use a named pipe, then the name of that pipe should be known to all the processes. Okay. And again, I mean, both unnamed pipes and named pipes, they behave like a FIFO queue. So this is a small code snippet just to show how such named pipes are used. First of all, see, just like a file, you have a name like this. Okay, you have a name. And this name should be known to all cooperating processes which want to use this pipe. So one process creates the pipe using the system called make FIFO. Okay. In fact, name pipes are called up FIFO. Main name pipes are also known as FIFO. So make FIFO, MK FIFO is the system call which will help you to make a, it's a system call. So you are basically telling the kernel that you want a name pipe. And then you have these permissions again, 0666. Once this pipe has been created, this name pipe, see one process opens this pipe as write only. So process A opens this pipe as write only or write only. This is a flag. And process B opens the same pipe. See, the same name is being used as O read only. Okay. After that, the producer will just write, and when it has done, it will close the pipe. The consumer will simply read from the pipe, and once done, it will close the pipe. Right. So, yeah. So basically, your program can even think that it is writing to a file, but actually it's a FIFO or a named pipe, which you have to create using a system call. Yeah, once you have created a FIFO special file, any process can open it for reading or writing the same way as an ordinary file. Of course, the name of the FIFO needs to be known to all the processes which want to use that FIFO. Also, another restriction is there. It has to be open at both ends simultaneously before you can proceed to do any input or output operations. Like it should not be that only one process is writing to it, no one else is reading from it. That is not allowed. It has to be open at both ends. Read and write. Okay, so and as I said, so these mechanisms do not work over a network because some way assume that there is a common memory in which such shared data structures can be maintained, like a shared memory or a pipe. So there has to be a common memory which is available where such data or such data structures can be saved. However, if you are trying to communicate over a network where there is no shared memory as such, then you have to use sockets and remote procedure calls and so on. So those are being covered in your networks course. So the summary for this set of slides, and we discussed what is a process. Like we discussed about process control block, and then we understood a bit more detail about context switch. And then we discussed about queues. So the kernel is maintaining several queues. Like there is a ready queue for processes which are ready queue for those processes which are ready for execution. Then there are other queues which are storing processes which are waiting. Like every device has a queue, and processes waiting for that device are in that queue. Right? That we discussed. Finally, we discussed this inter-process communication mechanisms, specifically shared memory pipe, name pipe, and so on. Okay, so any questions? If not, we will just start the next topic. Yes, Nisarg, that is the idea. So yeah, if two processes are reading from the same pipe, then like whatever has been read, that using that mechanism like in, right, that we discussed during a producer-consumer problem. Using that kind of a mechanism, so those data which are already read by one process, they must have incremented the in, so the other processes won't read the same data anymore. Okay, any other question? If you want to ask a question, just write on the chat question. I can allow you to speak. Right. So yeah, if you want to ask a long question, just write question. I'll allow you to speak. But yeah, I mean, the only thing I request is that don't start speaking suddenly, because yeah, that kind of breaks my flow. You do not need, if you have a long question, you do not need to type it out every time. Just write question. I can give you a chance to speak. Okay, then let me yeah, start the next topic. We won't go into much detail, but yeah, I mean, let's start. Okay. Okay. So this is a topic which we have been hearing for long. We have talked about it multiple times. Today also we will start with a recap, but yeah, I guess, I mean, it's long overdue that we actually study scheduling algorithms. We have talked about it so many times. So let's do the recap today. I mean, actual topic might begin tomorrow, but yeah. So we know that CPU scheduling forms a central idea behind multiprogramming. And modern OS, like Linux or Unix, they switch the CPU among processors for better utilization. Also, I mean, apart from processors, there are also something called threads, which are lightweight processors. We will discuss them later. Also, they will come in your lab assignments and all. But for now, let us deal with processors only. So we discussed these terms. These are just recaps. That CPU burst is the actual process is, I mean, if a process is having a CPU burst, that means at this present moment of time, the process is being executed in the CPU. Now, IO burst means that the process is waiting for the IO to be done. And so when one process is waiting for IO to be done, we prefer that the kernel shifts the CPU or switches the CPU to some other process. So that is better utilization of the system. And a process alternates between CPU and IO burst. So this is typically how the lifetime of a processor looks like. Let's say it does some it has an initial CPU burst, and then it waits for input, maybe read from a file or something. That is an IO burst. Once it has read the data from the file, then it does some operations on that data, etc. That's again a CPU burst. Again, maybe it will wait for writing some output to some file or some device. So that is another IO burst. Again, maybe it will take in some more data and do something and so on. So basically, usually a process alternates between these CPU bursts and IO bursts. Right now, so all the processes, say at this present moment, there are many processors in the system, and all these processes are having some CPU bursts and some IO bursts. So the question is that how can you schedule the CPU bursts of different processes so that the CPU is utilized well? So we would not like the CPU to have much of idle time. Now, one question comes up is that usually how long is a CPU burst? Is it very long? Is it very short? So first of all, understand that short, long, these are all relative terms. If you see this graph here, see the first is the x-axis, that is the burst duration. Note that the unit is milliseconds. So we are talking about, and the maximum value is 40. Okay. So we are talking in that range. 40, don't take it sacrosanctly. There is no rule that a CPU burst cannot be more than 40 milliseconds. But usually we are talking of time periods in that range, a few milliseconds. Okay. So again, I hope you understand that a modern processor can do lots of operations in a few milliseconds. So actually having a say, CPU burst of 15 milliseconds is quite reasonable. I mean, the CPU will be able to do a lot of operations in a 15 millisecond burst. Okay. So when I say like short CPU burst or large CPU bursts, understand that we are talking in the range of a few milliseconds. Okay. So the question is, in general, how long are CPU bursts? Of course, there is a lot of variation, and what you see is a distribution. So this is, I would imagine this figure has been plotted by saying this CPU bursts over many different systems. Usually, how long is a CPU burst? So it's just showing a distribution. So if you see, the peak is here, say somewhere around say 4. So most processors across many systems, most processors usually ask for CPU bursts of time 4 to 5 milliseconds. But then there are some processors which maybe ask for a bit more time, like maybe 10 milliseconds, 8 milliseconds, and so on. So typically you understand that most processors ask for only small CPU bursts, because even in say 5 milliseconds, the CPU can do a lot of operations. And after that, maybe the CPU, I mean the process itself will not ask for any more CPU bursts. Rather, it will switch to an input operation. Or something like that. So now the key question in scheduling is that whenever the CPU becomes free, the OS selects one of the processors in the ready queue for executing next. And who decides which process in the ready queue will be executed next? This is decided by a part of the kernel called short-term scheduler, or sometimes called CPU scheduler. So again, recap, we discussed this, the process state diagram. So we are now talking about this part. Okay. So among the processors in the ready queue, one of them will be chosen by the scheduler. This is what we are discussing. And the dispatcher will actually load that chosen process into the CPU. And then it will become running. This is the part we are discussing. The scheduler and the dispatcher. So the scheduler, also formally called the short-term scheduler or CPU scheduler, that is the one which decides which process should be executed next in the CPU. That means out of the processes in the ready queue, which one will be allocated the CPU next. And sometimes this is the only scheduler in the system. So when we just use the word scheduler, we actually mean this scheduler, because often that is the only one in the system. Now, the short-term scheduler is invoked very frequently. As you saw in the couple of slides back, most CPU bursts are of time duration, say 4 to 5 milliseconds. So every 4 to 5 milliseconds, the short-term scheduler will possibly be called to decide which is the next process to be run next. And therefore, this scheduler must be very fast. So I hope you understand this philosophy, that if something has to be done repeatedly, then that better be efficient. So you cannot design a scheduler which takes 3 milliseconds. Because after every 5 milliseconds, if 3 milliseconds go for scheduling, then that is a big overhead. Okay. Right? So we want that CPU scheduler to be very fast because it will be executed once every few milliseconds. Also, just for completion, there is another scheduler also which OS books write about, that is called a long-term scheduler or job scheduler. This scheduler, job scheduler, or long-term scheduler selects which processes should be brought into the ready queue. So remember, towards the beginning of this course, we studied old generation systems where we said that there is a job queue and ready queue. So initially when jobs are submitted, they wait in the job queue. And then someone must bring a job from the job queue to the ready queue. So usually that is done by the long-term scheduler. So long-term scheduler is invoked much infrequently. So maybe not every millisecond, but let's say every second or even every minute. So it is fine if it is a bit slow. Like it is fine if the long-term scheduler takes maybe 20 milliseconds to execute. Okay. But a short-term scheduler cannot even afford that. A short-term scheduler must be very fast. Okay, so the long-term scheduler controls what is known as the degree of multiprogramming. That means how many processes will there be in the memory, or how many processes how many processes will there be in the memory. That is called the degree of multiprogramming. So there are officially these two types of schedulers, short-term scheduler and long-term scheduler. However, also for practical understanding, nowadays the long-term scheduler may even be absent. Nowadays maybe there is only this one short-term scheduler which schedules which process to execute next. Okay. But yeah, it is good to know about both these types of schedulers. Often books write about them and so on. Okay, so now this is an important question. Okay, from now on, whenever we say scheduler, we will mean that short-term scheduler. Okay, so that is basically, our only scheduler. Let's assume that is the only scheduler in the system. So henceforth, whenever we say scheduler, we mean that short-term scheduler. So now this is an important question. When is the scheduler called? So every time the processor needs to be allotted to some other process, the scheduler will be called. And when can that happen? Several cases as written here. So maybe a process was running and that makes an IO call or a wait call. So that means this process is voluntarily giving up the CPU and moving to waiting state. Okay. I hope you remember what the wait call is. We had discussed this earlier. Anyway, so when our process is running and it requests for IO or executes a wait system call, then the state of the process moves from running to waiting. So clearly this process does not want to run right now anymore. So the CPU must be allotted to some other process. Hence the scheduler will have to be called. Again, let's say a process switches from running to ready. So this can happen when there is an external interrupt. Let's say a timer interrupt or an IO interrupt. So what is the difference between the first case and the second case? What is the difference, the key difference from the perspective of the process running? From the perspective of the process running, what is the key difference between the first case and the second case? Yeah, exactly what Nisarg has said. So the first case was the process voluntarily giving up the CPU. And the second case is that it's involuntary. That means the process did not want to give up the CPU, but some other event happened, like a timer interrupt or IO interrupt, due to which the kernel started running. And that is why you see that in both cases, the process initially was running, but then the state to which it changes is different, waiting and ready. Also, there are other situations where the scheduler needs to be called, like a process switches from waiting to ready. The process was waiting, maybe for some completion of some IO or termination of a child. That event has occurred. Therefore, now the process is ready. So then again, the scheduler will have to be called to decide whether which process will run. Again, understand this, just because a process is ready does not mean that it will be the one to be running next. That the scheduler will decide which process will run next. And finally, a process can also terminate, right? So a process was in a CPU burst, it terminated, as in it executed the last instruction and it is done. So now, again, this kernel has the control, right? Because it has made an exit call, maybe let's say. So the kernel has the control, and the kernel is to decide which process will run next. So then again, the scheduler will be called. So in all these different situations, the scheduler is called. So now exactly the point which I asked and which Nisarg answered, a bit more on that point. So scheduling can be of two types, preemptive versus non-preemptive. Okay. What are they? Let's understand. So let's understand non-preemptive scheduling. This is the voluntary part. That means scheduling happens only when either a process switches from running to waiting or when a process terminates. That means what? Once the CPU is allocated to a process, that process keeps the CPU as long as it wants. Only after it voluntarily gives up the CPU by one of these two mechanisms is the scheduler called to decide which is the next process to run. Right. So this is only the voluntary part. So I mean the process is allowed to run as long as it wants. Only when it gives up the CPU itself, either by terminating or by asking for IO, etc. Only then is the scheduler run to decide or to hand over the CPU to some other process. Okay. This is the voluntary part. Versus preemptive scheduling. This is the involuntary part. The CPU can be forcibly taken away from a running process. For example, due to a timer interrupt upon completion of time slice. Okay. So preemptive scheduling is more efficient because clearly in non-preemptive scheduling, if you give the CPU to a process, maybe it takes 2 minutes to run. Let's say it's that kind of a process which hogs the CPU for 2 minutes. Then every other process will have to wait. So that is not very desirable. Therefore, preemptive scheduling is preferred, where the CPU can be taken away from a process and given to another process. However, there are some potential complications in preemptive scheduling which has to be taken care of. Let's say it may result in race condition. So what is that? Okay, I'm not going into very much details, but let's see. So maybe a process is doing something, maybe something a bit critical, and within that operation, a timer comes. Sorry, an interrupt comes. So the process was within this important operation. Suddenly an interrupt comes. The CPU is given to some other process. Later, when this process will again resume, certain things may go wrong. That is called a race condition. Maybe it was like, so just think about it. Let's say, okay, I'm giving a slightly inaccurate example, but let me keep things simple. Remember that producer consumer problem what we discussed. So say the producer is producing an item, it's writing it to the buffer. So there are two operations. One is actually writing that element to the buffer at the position say in. Second is incrementing in by 1. Now let's say the process writes the element in the buffer, but before it increments in, it is switched off. I mean, the CPU is switched to some other process. So now there is an item on the buffer, but in has not been implemented. Right. So these kind of things can occur if you are not careful. We will discuss mechanisms of how to prevent these things. But yeah, these kind of things can occur if you are doing preemptive scheduling. Okay. Animesh is asking, some other program reading from a pipe will also be a race condition. I did not understand the question fully. Animesh, can you unmute and ask?
So like how Nisar said, like if there's a pipe and someone else reads it, so those bits would be lost. So in would move ahead, right? So that part of the buffer would be lost. So if
Yeah,
one
if you
program
are
is reading from a
careful,
pipe.
if the person implementing the buffer is not careful, then those things can happen. Though I must say that I'm not sure if this is a race condition, because see, this is the definition of the pipe. Like, it's a FIFO queue. So if one process has read the items, you still want that item to be available for some other process. Maybe that is not how pipes are meant.
No,
If
no,
you
I meant that
if you
like
want
there's
a
a
special
pipe.
kind of pipe, see, if you want a special kind of pipe, which uh, I mean, with that mechanism that, you know, even if one process, so suppose you want a special kind of pipe which is read by 3 processes, and you want the item to be in the pipe until all 3 processes have read it, then I guess you got to construct your own pipe which follows these rules.
No, I meant that suppose there's a pipe between two programs and the program reading from the pipe is interrupted and then some other program is able to read something from the pipe. That will be a race condition, right?
Again, I am not sure if I would like to call this a race condition, because that is how a pipe is meant to function. If one program is okay, if I am misunderstanding your question, then tell me. But what I understand is some program is reading from a pipe. Now the CPU is switched to some other program. That program also reads from the pipe, same pipe. So then everything is happening according to the rules of the pipe.
Yes, so that was my question, but basically the intended effect was the first program reading. So like from what I know, race condition is like two threads trying to override the same thing, but I don't
Yes.
think this is the same thing. So
Yeah,
which is why I had this doubt.
yes. Yeah, so I don't think that if 2 processes are reading from the pipe, then the data, I mean, still data would be available to one process, I guess. I mean, that is the default action of pipe. So, I mean, if what is expected is happening, I guess you cannot call that a race condition. But yes, you are right that yes, if such overwriting occurs, then yes, it's a race condition kind of thing. Okay, so yeah, so in case of preemptive scheduling, unless you are careful, sometimes some, undesired circumstances come up. We will discuss about how to prevent these things a bit later in the course. Let's see. Okay, and finally, yeah, the last slide for today. So yeah, so basically, we discussed about a scheduler and a dispatcher. So typically, scheduler will select which process to run next or which process to allocate the CPU next, and then the dispatcher will give control of the CPU to that process, which is selected for running next by the short-term scheduler. Okay, so and we know again that that involves quite a few steps, like the context of the program, which process which was running previously needs to be saved. Then the context of this program, which will need to run next, should be loaded. Then, remember all these things are happening in the kernel mode. So then there needs to be a switch to the user mode, and then jumping to the proper location in the user program to restart that program. So all these things should be done by the dispatcher. And again, similar to the short-term scheduler, the dispatch latency should also be low, because scheduling and dispatching both together, we want it to be as quick as possible, because we want the CPU to spend most of its time running user programs. Fine. So yeah, so that is the scheduler and dispatcher. So now the big elephant in the room is how to schedule. So how will the scheduler decide which process to run next? So that we will start discussing tomorrow. Okay. Okay. So yeah, I'll stop here today. We'll continue tomorrow with this, that how will the scheduler decide which process to run next? Okay, any questions? Okay, if not, we'll continue tomorrow. Thanks. Thanks again.